So I hope I am audible and I hope the screen is visible.
Yes, sir.
Yeah, okay. So yesterday we started evaluating definite integrals. We use the improper one to figure out how the Cauchy residue theorem can be useful in evaluating certain real integrals. And we considered first one, in which we said that the if function is of the form px over qx and qx has the degree which is greater than equal to 2 of the degree of pz or px, and qx does not have any 0 anywhere on the real axis, that means that the function fx does not have any singularity on the real axis, then we can use this method and we evaluated integral I minus infinity to infinity x square over x4 plus 1 dx by converting it into a complex valued function of a complex variable fz, which is equal to z square z4 plus 1. And you can see, I mean, towards the end we got this result that this integral can be broken down into two parts, one on the real axis and another on the complex plane. And the complex plane part goes to 0. Now, some of you did ask, of course, how it goes to 0, and you have question about why it is 2 power different. So I would just show quickly, for example, for this integral, if one goes further, we will just look into the integral z square over z4 plus 1 dz. And if we would like to integrate over this CR portion, which is basically what we are doing, this is the second part of the integral. First part was the real axis minus r to r. If I want to take the mod of this, all I am going to show that the mod of this in the limit r tends to infinity will go to 0, and that's how we are going to basically show it. So what, let's just look into this function fz. If I take this guy, okay, not mod z square, so this should be mod z square over z4 plus 1. Now this is over the contour which we are taking. So CR. Now let's just say that this CR means that it has this radius R. So at the contour, so this mod Z square, you will see will always be bounded, mod Z square will always be bounded by this R square, which is the radius of the outer circle, right? And what about this mod Z4 plus 1? Now this guy will always be greater than equal to mod of Z4 minus 1. So this is where we are using the identity that the numerator will always be bounded by r square, which is of course the radius, and the denominator will always be greater than z4 minus 1, which is basically coming from this a square plus b square identity, that a plus b square is greater than equal to a square minus b square, and that is what we are using. So which means that this guy will be less than equal to what? So z square over z4 plus 1 will be less than equal to what? Knowing these two identities, the numerator will be less than equal to
R square.
R square
r square,
R
and what about
square.
the denominator?
C4 minus
R4 minus 1. Yeah. So this is about this portion which is the function. So now think about it. When we are saying this CR, z square z4 plus 1 dz, and if we take this, then we say that this is always less than equal to r square r4 minus 1, which is mod of this. And what about what is left? Integral CR over dz. What will be this guy? What will this guy be less than always? this integral CR dz. This, since this portion is already bounded by this r square over r4 minus 1. Quick. This is the integral, right? CR dz, which is a semicircle. Dz will always be, I mean, what this will be bounded by? This will be bounded by, if it were the complete circle, it will be bounded by 2 pi r. If it is not semicircle, then it will be bounded by pi times
IR.
pi r, right? So the whole portion, which is the second part of it, is bounded by this r square r4 minus 1 pi r. Why do we want to write down this? Because what we say that this integral is completely bounded by this term, and what is the behavior of this term in the limit r tends to infinity? That's what we are going to use. So what will be the behavior of this in r tends to infinity? So let's just see. This will be pi r cube over r4 minus 1. Divide both the numerator and denominator by r4. So this will become pi over r in the numerator, and the denominator will become 1 minus 1 over r4. Yeah. So what is the behavior of this as r tends to infinity?
0.
So the denominator, of course, goes to 1 as r tends to infinity, and numerator goes to 0. So that means 0 over 1, which is basically 0. Which is what we are saying, that the integral CR z square over z4 plus 1 dz goes to 0 as r tends to infinity. Since this is bounded by 0, of course, that means that this integral cannot have any value other than 0. So that's what we use. And here it is also clear to you that why it has to be 2 powers different, because if you see this term pi over r, this term is coming pi over r because you have 2 power difference. Had there been only 1 power difference, you would see that there it would be only pi. Do it for z square over z cube plus 1 and you will understand what I said. So this is how this guy is taken care of in this portion. Yeah, so that's what we use. Okay. Now I will just carry forward, I mean, what we were doing. Part 2, let's say something similar to what we have done. However, we are interested in evaluating integrals of the kind, let's say, minus infinity to infinity fx cos of kx dx. So last time it was fx dx, now it is this, or minus infinity to infinity fx sin kx dx with k greater than 0, a real positive constant, and fx is of the same form px qx with same conditions. So both the two conditions, no zeros for qx on the real axis, and the degree of the px should be less than equal to degree of qx uh, by a factor of 2. Fine. Now, of course, what happens in this case, this cos kx or sin kx term, if you think about it, this guy is going to have the maximum value of +1 and -1 minimum value. So this will always be bounded by plus or minus 1. And hence, whatever we said about the previous case, that when we are going to take this contour and we are going to have this r tends to infinity, that will be taken care of. So that is why, I mean, fx is equal to px over qx with same conditions as in A1. This is what I used as the last one, A1. I am saying this as A2. So how to solve basically this one with k greater than 0? In fact, you can think about solving this as minus infinity to infinity fx e plus minus ikx kind of integral. Yeah, because if I call this, let's say, as I3 and I call this as I1 and I2. So how I3 is related with I1 and I2? So if I just take the plus part, so there are
The
two.
sum of the two.
So I3 plus can be written as I1 plus what?
Iota I2.
Iota I2. Very good. And what will be I3 minus?
I1 minus iota I2.
I1 minus iota I2. So, I mean, we can actually think about solving this integral, or we can think about solving this integral. Then we can say that the first part, the cos kx, is nothing but the real part of it. Sin kx is nothing but the imaginary part. We have, of course, always of doing it. So, generally, it is customary to solve integral of the type fx plus minus ikx dx whenever we are solving integral of the type fx cos kx and fx sin kx. And then later on we say that, okay, let's just put the real or the imaginary part. Now, how do we solve it? We solve it using, of course, the complex integral, converting this to complex one. So we would like to do something where we would like to have a closed contour C, which should have this real portion going from minus infinity to infinity. And then again, we can think about the semicircular one. I've said, let's say EIKZ. Of course, we can do E minus IKZ also, but I will discuss about it later. So we can think about solving this FZ EIKZ. Now, can somebody tell me what is the maximum value which EIKZ takes? Or what is the value of the mod of EIKZ? What is this?
Sir, 1.
Sir, 1.
Yeah, this is something where you have to be clear that we are using z, which is a complex variable, right? That means we are talking about EIKZ is equal to EIK x plus IY, right? So which will be this EIKX and then minus ky. I square is equal to minus, and that means minus ky. So what is the mod of EIKZ then? This will be equal to mod of EIKX and mod of this guy. The first portion, of course, goes to 1, right? But what about this guy, e raised to a minus ky? If k is greater than 0, then what happens to this term? And if k is less than 0, then what happens to this term? So the term which is there. So this is basically we are left with e minus iky. So tell me. So case number 1, k
Sir,
greater than
if
0.
k is greater than 0, then its value will be less than 1.
No, not all the case. If k is greater than 0 and we are on the positive side or the
Yes, sir. Positive side.
upper hemisphere, then in that case this guy goes to, as y tends to infinity or as z tends to infinity, what happens to this?
It will go to 0.
So this guy goes to 0. What about if k less than 0 and we are doing imaginary y greater than 0? That is, had this k being less than 0 and I would try to see it in the upper half, then what will happen?
Infinity.
This goes to infinity, absolutely, which means that my function is no longer bounded. So please see that if I am going to select my k greater than 0, then only way I am going to solve it is that I am going to solve it in the upper half. What about if I take k greater than 0 and this guy is less than 0 in the lower half?
Infinity.
So this is imaginary y. Okay, I mean, in principle, this is imaginary z, which is what I am writing as y. Yeah. Yeah, this guy again goes to infinity. And what about if this k is less than 0 and I am talking imaginary z, which is nothing but y, this less than 0. This goes to 0. So these cases defined that what kind of contour I am going to have. In the previous case, I told you A1, the problem can be solved by choosing contour in the upper half or choosing contour in the lower half. It is just that you'll have to be consistent, whether you are using plus 2 pi I or minus 2 pi I. But in this problem, you cannot arbitrarily decide to choose anything once k is defined. Now, what is defined in our question? K is greater than 0.
Greater than.
That means that what kind of contour we can now think about having. Because I want to go from minus infinity to infinity, so I will use, of course, minus r to plus r. So you will have, of course, contour which is going like this. And now what?
Sir, upper hemisphere.
Since
upper half.
k, so the only way this you are going to solve is that you are going to choose a contour in the upper half. If you choose the contour in the lower half, then our result will not remain valid. So this is the additional thing which you want to see, which you want to have as compared to our previous problem. Other than that, solving this problem is similar to doing the problem what we have done in the past one. So let's just take an example, do this question, and then I will let you ask question. So I ask you to evaluate minus infinity to infinity cos kx dx x square plus a square, where k and a is greater than 0. In fact, I could have asked the same question in something like minus infinity to infinity sine kx over x square plus a square dx. I could have asked this question as well. It's one and the same thing basically solving there. So how are we going to tackle it? We will first use the complex form. So complex form of this function, that means we are going to choose fz is equal to eikz, and that is why I said that it doesn't matter whether we choose cos kx or sine kx. And then z square plus a square. And then writing c eikz over z square plus a square dz, where c is a positive oriented contour which is chosen in this manner the way we have decided. And so let me just write CR here. So I can write down now minus r to r, since it's only on the real axis. So I can just write down this guy x square plus a square plus CR eikz z square plus a square dz. And in the limit r tends to infinity. In the limit r tends to infinity. So what will happen to the second term? You have already seen what happens if 1 over z square plus a square is there, right? That is what we have already got. Eikz will be behaving like this e minus ky, which also goes to 0 as r tends to infinity. So this term in fact will fall sharper than the previous term to 0 in the limit r tends to infinity. Exactly in the same manner in which we did the last one, except that we have this additional term coming up to be e raised to power minus ky, and k is greater than 0, which will also go to 0. So this is what we are going to solve. So how are we going to solve this now? The left hand side using the,
Sir, the residue
Residue
theorem.
theorem.
yeah, so let's just apply. Please apply residue theorem and then give me the answer. So what are the singularities?
A iota and
Plus
minus A
minus
iota.
iota A.
Plus iota
Plus
A and
minus
minus iota A. Which one do you choose in this case? Residue, are you going to find out for
Plus
both?
iota A.
Sir, A
So,
item.
plus A.
right. So plus iota A, that means it will be on the imaginary axis. So it is this. Another one is minus IA. So you are going to find out the residue for 2 pi I times residue at Z is equal to IA. Which of the method you are going to use? Simple pole or pole of some order?
Simple pole.
Simple pole.
Simple
Good.
pole.
Simple pole.
Great, great. So give me the result of the LHS. So that means limit R tends to infinity minus R to R E I K X, okay, I x square plus a square dx is equal to 2 pi I residue z is equal to IA of this fz. Got it?
Yes.
What's the residue?
Pi e to the power minus Ka by A.
E raised to power
Minus Ka by A. Not 2IA.
minus. Okay, let me just write down the full
2AI.
2AI, right?
Uh.
Okay. So can somebody else also confirm it? Two of you have already said that. Yes, no?
Yes, sir.
And the result will be?
Yes, sir.
Good, very good. So it is pi over A e raised to power minus, sorry, Ka, right? So now,
Yes.
this is the result. And what will be this minus infinity to infinity cos kx? Now the question coming back to this, x square plus a square. And what will be sine kx? Dx over x square plus a square.
So the cos will be the term which we got, and the sign will be 0 because there is no imaginary part involved.
So sine will be 0. But sine term you would have actually told me even earlier, right? I mean, you would have given me this result even before we had proceeded, right? Yeah, the function is an even function of 1 over x square plus a square is even. But what about sine kx? Is this an even or an odd function?
Odd function.
Odd
So
function.
overall
Odd
this
function.
function is what? An odd function integrated from minus infinity to infinity. You would have given me 0 anyway, right? But this also gives me one more point that I could have asked this question for the even functions in terms, or odd functions in terms of 0 to infinity also. Yeah. So what would have been the result for 0 to infinity cos kx dx over x square plus a square?
Pi by 2A into the power
Half of
minus
it.
Ka.
So half of this, absolutely right.
Half of.
Right. So please see that these are second kind of integrals which we can solve, again the improper integrals which we can solve using this contour integral or the using calculus of residues. Yeah. Okay. Questions here. Okay. I hope that you are clear with the contour which we have chosen, because we have an option of giving the same question with k, for example, less than 0. And then what you would have done in order to think about the contour?
The lower hemisphere.
To choose in the lower half of the plane.
Lower half, right. So in that case, you would have chosen the lower half of the z-plane or the Argand diagram in order to solve it. So that is the only difference it comes. However, make sure, I mean, even though the results might look similar to you, but it is very important to choose our contour properly. We cannot just arbitrarily decide to choose the contour. The simple reason is that the second term going to 0 is dependent on choosing that contour properly, just like the way we saw it in our previous example. So now extending further, A3. But now thinking about, so EIKZ, FZ, DZ, this is coming from our previous example only, but now thinking about this guy. Up to now we were saying that our fx should be px over qx with the degree of qx should be greater than or equal to degree of px plus 2. But as soon as this EIKZ was added to this function, I should not be worried too much about this 1 over the greater than 2. What I should be worried about is the following, that whether fz goes to 0 as r tends to infinity or not. I should not be worried about rest of it. Why and what am I talking about? Let me just quickly tell you. So look into this function or integral which we are writing and which goes to 0 basically. Look at this again, EIKZ FZ DZ. Can somebody quickly remind me, when we were doing this A1, why I ask you to take 2 degree more and not 1 degree more? Can somebody remind me?
Sir, so that the part which the CR part which we consider, it goes to 0, so that we get 1 upon r kind of a dependence and it goes to 0.
So there we were worried about FZ DZ together. But now I should not be worried about FZ DZ together, as I already have this EIKZ. And this is the portion which comes as what is called as Jordan's lemma. Now what is Jordan's lemma? That I do not need Px with over Qx with Qx degree at least greater than or equal to 2. Or because when I am talking about this EIKZ, remember this EIKZ goes like E minus ky, which for k greater than 0 and y of course greater than 0 goes to 0 exponentially as r tends to infinity. Yeah. So now think about how this EIKZ times DZ is behaving. EIKZ goes like E minus KR as R tends to infinity. DZ goes as, sorry, not 1 by R, it goes as R. So DZ grows as R and EIKZ exponentially decays as x e minus kr. So now for these two, whenever k is a positive constant, any positive constant chosen, this term goes to 0 as r tends to infinity, because the exponential die out is far faster or sharper than the growth, linear growth. So one we are talking about the die out and another we are talking about a linear growth. So since the exponential function grows e minus kr and this is proportional to r. Since we have the EIKZ takes care of my DZ, all I need to think about whether my FZ goes to 0 as r tends to infinity. If that happens, then Jordan's lemma basically tells us that limit r tends to infinity, EIKZ FZ DZ over CR goes to 0. So the condition is now relaxed to FZ goes to 0. All I need to check is this function if this fz goes to 0 or not. So if it is of the form, let's say px over qx, then what kind of degree you are now thinking about? Earlier we were saying that Qx should be having 2 degree more. Now, in view of this Jordan's lemma, that
So just
growth
1 degree more will work.
1 degree more would be enough.
1 degree more.
exactly. So now you will see that you would be able to solve problems of the kind Fz is equal to Pz over Qz with degree of Qz greater than or equal to degree of Pz plus 1. So Jordan's lemma added this portion to our arsenal of integrals, that I do not need to now worry about 2 degree difference. I can now think about any function fz which goes to 0 as r tends to infinity, because rest of the thing will be taken care of by this eikz. At this point, I will also tell you that several times in the Viva, this question is asked, of course, if eikx, how does this guy behave if k is positive constant and x is a real number? And then immediately afterwards, this question is asked how this mod of eikz will be. So make sure that you understand that it is a complex variable. So just divide it into 2 parts and then tell that this is how it is, that it's if k is a positive one, then it will decay. If it is k is a negative one, then it is going to grow. So just remember that. Okay. With this, I would just leave this one. Another question for you for this portion, which will be what? Now I can ask question like this: x sine, or my sign is not looking good. X sine 2x dx x square plus 3. It's an odd function or an even one?
Even.
X
Even.
times sine 2x over x square plus 3. So I can now ask you to evaluate this 0 to infinity. And this is, let's say, a question for the homework. It is now you can see that x over x square plus 3. If I convert it into z into ei to z divided by z square plus 3, then correspondingly you understand that what is happening here, right? I mean, z over z square plus 3, only 1 degree difference, but this goes to 0 as r tends to infinity, and rest of the thing will be taken care of by this ei to z times tz. So this is what you are going to solve using calculus of residue, and now you'll have to think about whether you are going to convert it to minus infinity to infinity, and then later on you are going to do 1 over 2 of that, or what you are going to do. Please try to do it as a homework problem. Okay, questions till now. So we have done A1 kind of integral, fz or px over qx. We have done A2 kind of integral, again px times qx, but now multiplied by exponential of some ikx or exponential of minus ikx, where k can be greater than 0 and k can be less than 0. The important point of difference is that we'll have to now choose the contour which is only one contour. In the case A2, there can only be one contour which will be giving you the correct answer. Another one, the second term will not go to 0. In fact, it will grow infinite, and hence you cannot use that. In the first case, A1, you could have used any of the two. By the way, did somebody try to use that? The lower half of the Argand diagram to solve our problem 1? Okay, just attempt it so that you understand that choosing a contour, how do you decide on doing that? And A3, we just relaxed the condition of px over qx, nothing beyond that. We need that fz should go to 0 as we approaches as r tends to infinity. Yeah, so that's still important, and there should not be any singularity on the real axis. As soon as the singularity comes on the real axis, you have issues, of course. Okay, then there comes this interesting kind of, yes.
Sir, on the last page, there was a graph that you made.
Okay,
Could you
previous
just
one.
explain that once more? Yeah, this side.
Yeah, I mean, I did a little bit faster, but yeah, okay. So So remember, this is r, which is nothing but the radius of the semicircle which we are using, and we take the limit when r tends to infinity. So if I want to plot function e minus k times r and function r, so we have two terms, e minus k r and another is r. How e raised to power minus k r decreases as r increases. So this is exponential decrease, right?
Yes, sir.
And how this r, which is a linear, this, how this increases, this of course is a linear increase.
Linear graph, right?
So this is a linear graph. Now this guy grows as r tends to infinity, and this guy attenuates as r tends to infinity. There is a competition between the two. Which will win the competition? The exponential die-off is always much faster than the linear increase, and hence it is the exponential die-out which will always win. And that is why it is said that the exponential attenuation of the function will compensate for the increase in r, such that the combined result will always go to 0 as r tends to infinity. That is what the Jordan's lemma was. And hence this dz portion of our integral, this guy will be taken care of by this eikz guy. So all we need now, that if fz tends to 0 as r tends to infinity, then the limit r tends to infinity, this kind of integral which we were using in our previous A2 problems, this will go to 0. So we do not explicitly need this pz over qz to have the degree which is different by 2. Fine. Is it fine?
Yes, sir. Now it is
Okay.
fine. Thank you.
Good. Good. Okay, now B1 kind of
Sir.
integral, why I put it as B? Yep, please ask.
If both the poles lie inside the semicircle, then will it be of order 2?
No, no, it is not about both the poles. Each pole has to be figured out of an order, right? I mean, z minus I square, what kind of pole it is? Is there any pole?
Sir, a pole of order 2
And pole is
at iota.
at plus
Iota.
iota or minus iota?
Sir,
Plus
plus
iota.
Okay, and then if I have this function z minus I square, z minus 2i. So how many singularities, what nature?
sir, two singularities. One
Sir.
of one a pole of second order and other one a simple pole.
Okay, so you have one at here plus I and another it at 2i. So this guy is of order 2 and this guy is order 1. So it doesn't matter. I mean, how many singularities are there? You should be knowing the nature of each of the singularity, and hence you'll have to solve for your residue. If there are more singularities, then it is just the sum of those residues, right?
Okay, sir.
Yep. Yeah. Good question. So remember, the residue theorem does not worry about how many of these. As long as it is finite, it is fine. As soon as it goes to infinite, then there is some issue which I am not even talking about. So finite singularity, it will be taken care of. So why I call it B1 kind of things, or in fact for B I have only this one, because these questions comes of this form. Very different from the proper integral which we were saying minus infinity to infinity or 0 to infinity. They are of the type 0 to 2 pi f of cos theta sin theta over d theta. And generally these kind of questions are solved by, again of course we will go for our complex integral, but just by choosing mod z is equal to 1, that means z is equal to ei theta. Remember this deformation of path, so we can always choose some appropriate contour. We'll discuss it soon, but it is z is equal to ei theta. As soon as I understand that or I remember that, I can write down what will be e raised to power minus I theta, and then I can write down what is cos theta, which is nothing but, right? So what will be e raised to power minus I theta if z is equal to e raised to power I theta?
So Z bar.
Or since I want to play with z only, so I will just write 1 over z, right?
Yes, sir.
Yeah, I
Yes,
mean,
sir.
remember that the
Yes.
analyticity demands that you try to work only with z's. Anything with respect to z bar, your analyticity has an issue. This is something which we discussed in the beginning, that del f over del z bar is equal to 0 is what we used as the Cauchy-Riemann condition. And we said that function, if it is analytic, has to be in terms of x plus I y and not in terms of x minus I y. Although your answer is right, z bar, but what we want is always the function of z, and hence we are going to use this 1 over z. Okay, so cos theta, yes.
So, can you explain why are you writing power minus iota theta is equal to 1 by z?
I mean, if z is equal to e I theta, so 1 over z is what?
Oh, yeah. Sorry.
So this is fine. I mean, the problem is not about this. The problem is about, can I write like this and then solve it? Then I will have problem, because then I never know what to say about the analyticity of the function. Since my function cannot be a function of z star if it is an analytic function, hence we will avoid writing z star anywhere. Otherwise, we'll have to keep on checking whether this function is getting converted into the analytic function or not. Can I get rid of this z star or not? So instead of that, we will just avoid writing z star. Every time you see analytic functions, you will say that you do not want to write it in terms of z bar. Again, the complex form of our CR equations. Yeah, but okay, cos theta, what will this become? Z plus
Plus 1 by
Plus 1
1
z.
by
by
z.
Z by 2.
z over 2. What about sin theta?
Z minus 1 upon Z by 2
Z minus 1 by
minus
z
1 by
by
z
2
Z
iota.
minus 1 over z,
upon 2.
very good, upon 2
Upon
iota. Right. And what will be your d theta if z is equal to e I theta?
dz by iota e to power iota theta.
dz over,
By iota
okay, iota e to
e
power
iota
I
theta.
theta, and that is nothing
Yes.
but z.
Z.
Okay, so
Yes.
let me just quickly see if you are able to write down this guy. So let me just give you something. A problem 0 to 2 pi, let's say, d theta over, let's say, root 2 minus cos theta. If you have to solve a problem like this, it doesn't seem like a simple problem if you are going to use the real one. However, if you just convert it into your complex plane analysis, so we'll just convert it into something like this. And then I would like to write everything in terms of z. So what should I be writing? D theta should be dz over
dz
iz.
plus
This
z.
is what you told me. Root 2 minus z plus 1
Z plus
over
1 by
z
z.
over 2 C unit circle positive oriented. Oh, pause. Oh God. Yeah. Okay. Positive oriented unit circle. So this is what we are doing. Now, can you just simplify it and give me some equation in terms of dz over what? And there may be some other constant also. So any
2
constant with
by
which
iota
everything is 2 by iota. Okay. And then
and divide by 2 root 2 z
2 root 2
minus
z
minus
minus
z square minus 1.
minus z square minus 1, which means you can write down as minus 2 over I this mod z is equal to 1 dz since it's a quadratic equation, so I will prefer writing like this, right? Right?
Yes.
Yes, sir.
And that means what? You are supposed to find out what kind of singularity do we have in this function, and whether the singularity is lying within this mod z is equal to 1 or not. So this will be your contour. Since you are going from 0 to 2 pi, now this question will be whether we are going from 0 to 2 pi or not. You can go from 0 to pi, and in that case you will have to again start thinking about these semicircles, etc. But the problem is now reduced to figuring out if there exists any singular. Okay, now this guy is 0 and this guy is 1. So this is a unit circle. Okay. So that's what we do in order to solve problem like this, which are related with the trigonometric functions. So several of the trigonometric functions are solved using complex integrals as well, just like we are solving the improper integrals like this. So this is basically again complex integrals or the calculus of residue can be useful in solving problems like these ones. Yeah. And I still have one more, which is okay. I mean, in principle, it is extending my A3, but why I wanted to do it at the end, because this is something like singularity on real axis. Now, this kind of either we have the real singularity or we may have apparent singularity, but somehow we have singularity on the real axis and we want to solve problems like this. Now, in these problems, it is possible that I may not be getting the actual integral value anytime. What does I mean to say by what do I mean to say by that is that I will be solving surely for Cauchy principal value.